Hello everyone and welcome back for the DMS lecture. Today we'll discuss problem number 2 for belt conveyor design. In previous problem we have seen the full design, and in this problem I will show you some few shortcuts so that you can do your design with minimum possible time. Okay, let's see with the design. What is the problem statement? A 20-degree troughing belt conveyor has a following specification. Material to be conveyed, that is a limestone. Maximum lump size is 100 mm. Capacity is 300 ton per hour. Inclination, that is a 10-degree. And center distance is 60 meter. Okay, what we need to be calculate, or what we have to determine? First, determine the width, number of plies, and the thickness of belt. Second, select a proper motor for conveyor. And third, the design of drive pulley along with its shaft and bearing design. Okay, so initial first step of this any design is to note down the input data. So the input data, that is a material to be conveyed, limestone, maximum lump size, which is denoted by small a, is equal to 100 mm. Capacity, capital Q, is equal to 300 ton per hour. Center distance, capital L, 60 meter. Length of angle of troughing, that is approximately 20-degree. Angle of inclination is 10-degree. Now in figure 1, the schematic layout of the belt conveyor arrangement as shown. Okay, where I have shown the main components. Basic assumptions for any design we have. Okay, for belt conveyor, initially we are considering that the unload takes place at a higher location. So it means that the material flow from lower side to upper side as shown in figure. Angle of lap at the with the help of snub pulley, that will be handled is about to 200-degree. So using snub pulley, if you look at in a figure, it is shown it properly over here. With the snub pulley, we can increase or decrease the angle of lap. Okay, so whenever you are going start with the design, you must have to draw this schematic layout so that the examiner or any person who can see in your design, it will understood what kind of design, which type of mechanism or what kind of the system you are designing. Let's see next point, calculation of belt width. So here P is equal to X into A plus 200 mm. So there are two type of material. One is the graded material or another is a ungraded material, where X is the coefficient for that material grade. We are selecting ungraded material so that whatever the capacity or we can the strength which is we can select or calculated, that should be the lesser one. Okay, so it is only empirical relation. If you okay select graded one, it will give another value. Okay, so let's see, we will select ungraded material. X is equal to 2.5. Putting the values in equation, B is equal to 450 mm. Okay, this is an empirical relation. From a PhD page number 9.18, the equation is given: B minimum is equal to 1.11 Q divided by rho CV square raised to 1 half plus 0.05. Uh, Rather than selecting first one, you can go with the PhD page number 9.18 so that you can easily calculate the actual belt width or minimum belt width. Rho, the density of material, as we are conveying the limestone, The density of material is 1.35 ton per meter cube, referring PhD page number 9.22. Second, C. C is the factor for type of idler. As we are using troughing idler with the angle of 20 degree, the value of C is 460, referring PhD page number 9.18. There is a column. In that column, it is shown. Q, the conveying capacity, that is a 300 ton per hour. Velocity, uh, velocity is not given in example, or you can say problem. So initially, with the lowest and the highest velocity, which is shown in page number 9.20, out of that, we are selecting the lowest velocity for basic trial, that is a 2 meter per second. Now put these values in equation B minimum. What we get? Minimum belt width we get is 601 meter. That is 601 mm. Now when we comparing first and second, that is first is a empirical relation and second one is based on the actual data. So second one is giving a higher value of belt width and we are selecting that higher value. So this is a standard, okay, and selecting the standard belt width, that is B is equal to 650 mm from PHE. Next, calculating the actual velocity. As the belt width changes, the velocity get varied. So we are putting the B minimum value is 0.5. It is in a meter, and the velocity which is calculated is, or actual velocity is 1.68 meter per second. But when we compared with the limestone application and the belt width, that is 650 mm, the maximum allowable velocity is 3.5 meter per second, and calculated or actual velocity is 1.68. So our design is safe. You can refer with the PHE page number 9.20. Next one, calculating the resistance of belt for upper run. Okay, referring PHE page number 9.18, we got an equation W0 is equal to CFL into bracket GG plus GB cos of delta plus GRO plus H into GG plus GP. Okay. Now we need to calculate these values. Value of C, that is a secondary resistance factor, which is shown. We need to calculate from the graph, which is in PhD page number 9.18. So from that graph, we found that C is equal to 2. Then a friction factor for standard conveyor, it is 0.02, which is also shown in PhD page number 9.18. Length, which is given, that is 60 meter. GG, that is the weight of conveyed material per meter, which is in kgf per meter. Now it has to be converted. So for that, the formula which we have calculated, we use, that is Q multiplied by 1000 divided by 3600 and the whole term divided by velocity. So 300 multiplied by 1000 divided by 3600, the whole term divided by 1.68. So value of weight of conveyed material per meter is 49.6 kgf per meter. Next one, GB, that is a weight of belt meter uh, length, that is 9 kgf per meter. Next one, to calculate the value of GRO, that is the weight of troughing idler on the top run per meter, referring page number 9.19 with the table number 2. As previously I have was shown the procedure, how to select those things. So here also we are selecting the tube diameter is 125 mm and the bearing diameter is 20 mm. For the bearing width, belt width B is equal to 650. The weight per assembly is 17.9 kg per idler assembly. A row, as we have already noted down, that is 1.35 ton per meter cube. And the maximum spacing, which is referring with the help of PHG 9.19. For upper run, it is 1.5, and for lower run, it is 3 meter. Okay. Weight per meter, that is GRO, that is equal to weight per assembly divided by spacing. So weight per assembly is 17.9, and the spacing, maximum spacing between two roller is 1.5, as we are designing it for upper run. So it is 1.5. So value of GRO is 11.93 kg per meter. Okay. You can, while calculating, you can pause the video and you can select the appropriate values from PHG. Now next one, to calculate the height of trough, which where the material is to be conveyed, H is equal to L sine delta 60 into sine of 10 degree. So H is equal to 10.42 meter. Considering positive sign for conveying material up, because it is very important. If you conveying the material down, the sign that is considered is negative, and when you material conveying up, we have to consider positive sign, which is the note is given below the page. Now putting all the value of CFL, GG, GB, GRO, what we get, the W0 is equal to 777.75 kgf. Okay, so the maximum resistance of the belt on the upper run, that is 777.75 kgf. Now similarly, you need to calculate same resistance for lower run. Referring page number 9.18, equation is given. WU is equal to CFL GB cos of delta plus GRU plus minus or minus plus H into GB. Now here CFL values are known with us. GRU, that is a weight of straight idler on the bottom run. Referring page number 9.19, for straight idler, the idler weight per idler assembly is equal to 11 kgf, and the maximum spacing is 3 meter. As I previously said, for upper run mostly it is 1.5, and for lower run it is mostly 3 meters. So next, calculating the value of GRU. GRU is a weight per assembly divided by maximum spacing between two rollers, that is 11 divided by 3. GRU is equal to 3.67 kgf per meter. Now here we are considering negative size sign because we are conveying the material in upward direction. W U is equal to minus 63.7 kgf. One very important note I would like to share over here. The value of WU is always, or you can say must, negative for whenever the material is conveying up, and whenever the material is conveying downward direction, it is in a positive sign. Next step, calculation for effective pull on the belt, that is denoted by P. So the P is equal to WO plus WU, referring PHP page number 9.18, 777.75 minus 63.7. The effective pull on the belt P is equal to 714.05 kgf. Next step, to calculate the maximum tension in the belt. referring page number 9.18, equation is given for assuming the header drive T1 is equal to P into e raised to mu alpha divided by e raised to mu alpha minus 1. So value of mu we are assuming is 0.25 by referring page number 9.18 where the range of mu is given. T1 is equal to 512.5 kgf. As we know that the value of alpha, that is the angle of lap, is 200 degree. We have converted into the radian. Next one, calculation for minimum tension in the belt, that is T2 for a driving head. Similarly, with the same column, you can refer page number 9.18, but there is a one condition. You must satisfy the condition that P divided by e raised to mu alpha minus 1 is always greater than the h into gp factor. So we need to see whether it is greater or lesser. Okay. So first of all, calculate p divided by e raised to mu alpha minus 1. Okay. So putting the value of p mu alpha, what we get? The value of that ratio is 512.5 kgf. Okay, which is we given and denoted by a. Now second equation, h into gb, it counts up to the 93.78 kgf, which is denoted by b. From a and b, as per the equation, the value of p divided by e raised to mu theta minus 1 should be greater. And from a and b, when we compare, it is this condition is satisfied. So after the satisfying this condition, we can choose a formula T2 is equal to T1 minus P. So T2 is equal to 512.75 kgf. So minimum tension in the belt for driving head is 512.75 kgf. Now next one, calculating the number of plies. Referring page number 9.18, I is equal to T1 divided by B into F. Now here the value of F is different. So working tension of the belt per meter, width per ply, that is in a kgf per mm. Refer page number 9.12, table number 5. As the material or sorry, as the material density is greater than 1.2 ton per meter cube, we have to select the designation of the belt conveyor is 63 OZ. Okay, and it is jointed by using vulcanization joint process. Also, we have selected over here the take-up system is used is a gravity take-up system. Okay, that gravity take-up system I have drawn, or you can say schematic diagram of that arrangement I have shown at the end of this problem. So the value of F is 0.71 kgf per meter per ply. Putting the value of T1, B and F, the value of I is equal to 2.66. But the allowable or allowed maximum and minimum number of plies for OZ 36, or you can say 36 OZ belt condition, referring page number 9.21 and table number 4, that is 5. So calculated value is a lesser one. So we are selecting the modified value of number of plies is equal to 5. Okay. Next one, calculation of diameter of pulley. So dp is equal to kpl into kp into I, where kp is a general value of coefficient depending upon the strength of the ply fabric. In previous problem I have given that table. So from that table we are choosing the value of 140 kp, the coefficient depending upon the type of pulley. Here we are choosing the crown pulley, that is the value of kp is 1.1. So the diameter of pulley dp is equal to 770 mm. Next step, the calculation of width of the pulley. Okay, for that you can refer page number 7.54, where the standard pulley, to calculate the width of pulley, the standard equation is given. W is equal to B plus 50. So value of B, that belt width, is equal to 650 plus 50. It means that the 25 mm from each side, it gives a margin so that the belt can be set it properly. So the value of W is equal to 700 mm. Okay. Now next one, calculating the bearing pressure of the pulley, considering the head drive pulley mechanism. So for that, P is equal to T1 plus T2 divided by pi dp B into alpha divided by 360. So putting all the values, we can get directly P is equal to 0.01953 Newton per mm square. So that much bearing pressure is occurring. And for standard bearing pressure, that is 0.4 Newton per mm square. So the whatever the bearing pressure occurred in actual conditions are very far less than the than the design condition. So our design is safe for bearing pressure criteria. Okay, now selecting the motor. To calculating the motor power, the equation Ka into P into V divided by rho efficiency of driving mechanism. So K is the coefficient of adhesion between belt and roller, that is considered as a 1.2. P is equal to effective pull on belt, which we have already calculated. V, the belt velocity, which is in meter per second. So, and we are considering the driving efficiency is 85% because there is a loss of power due to the sleep and the other phenomena. So that's why we are considering 85% efficiency of the drive. So putting all the values, what we get, the P power for motor, P is equal to 16,613.8 kilowatt, 8 watt. So by using page number 5.124, we have to select standard motor, that is a 3-phase motor. Okay, and our power calculated is 16.61, we have to select more than that. So the standard capacity of the motor, that is 18.5 kilowatt with the motor speed of 1500 rpm. So these are the standard values, or you can say you can note down the frame number and other part. If you want, you can draw a simple schematic diagram, because we are using coupled motor. Okay, next one, the calculation, they select standard speed reducers. Whenever we are going to design a gearbox for same mechanism, belt conveyor gear reduction ratio, so for that we need a speed, or you can say reduction ratio. So initially calculating the total reduction ratio, or you can say overall reduction ratio. For that, we need a speed in RPM. As we have a velocity of 1.68, we can convert it into speed. that is v is equal to pi dn by 60. Calculating the n is equal to 41.67 rpm. Now overall reduction ratio, that is nothing but output sorry input divided by output, so that you can get a proper reduction ratio, that is 36 approximately. So it is not possible to reduce that much power in a single stage with the help of a spur gear, helical gear. Okay, so we need to convert these into two stage reduction. So selecting spur gear, we can make a square root of same, so that we calculate the value of first step reduction ratio, that is 66.3, and for second it is 5.71. Okay, otherwise you can take a square root of I, so that you can directly get the value of I is equal to 6. Okay, referring page number 8.3. For this calculation we are referring page number 8.3. Okay, so thank you very much. In today's lecture we will discuss that much. The remaining design of the shaft, then pulleys, sorry, rather than pulley I can say the troughing idlers, and the design of shaft for same. Okay, that will be we will discuss in next lecture. Okay, if you have any doubt, you can feel free to contact me. Okay, and try to complete this design with the help of phd, so that you can properly aware, or you can say you will have a proper practice to use a phd for design purpose. Okay, thank you very much.